Remo, for the nice introduction, and good morning to all of you. I feel like I'm sitting in a small Norwegian town. That many people. It's it's nice. Today I will be talking about what Alan said. When colors aren't enough, the power of spectral imaging. So this has two parts. In the first session or first half, I will talk a bit of basics of the spectral imaging. And in the second half, I will talk about more in the application towards agriculture and also cultural heritage. These are the two application areas I actually work for my research. A little bit about where I'm coming from. So I come from NTNU, Norwegian University of Science and Technology. This is the largest university in Norway with around 44,000 students. And And within the university, the Department of Computer Science, we have around 300 plus employees, and which includes PhD students and professors and academic staff. And in Department of Computer Science, there are 6 groups, and I belongs to a group called the Colourlab, which has around 50 people. And in Colourlab, the main research focus is actually focused towards the color management, why the color is not consistent between different devices, and that you would have already experienced in real life in different instances. And not only focused on color, but also extending color to different application areas, not only in cultural heritage and whatever listed here, but also wherever color present. I just want to mention about one of the courses that we are actually starting in this autumn, and whatever I'm talking today in my presentation will be part of this course, this master's program. So those who are looking for a master program to specialize on visual computing or visual informatics, it's a nice opportunity to join. So this is the outline of the talk today. As I said, I start with the color, spectral imaging, and some basic concepts. And then we do a Kahoot as a break. And then we go for the application areas. So color, everyone knows what is color. And wherever you look around, you see color. That's a basic perception, the fundamental thing that you actually see from your birth, or slowly after birth you learn. And color is something happens between the eye, the object, and in the processing happens in the brain. So you experience and you evaluate different things based on the color. So for example, you choose a food, and you even without tasting it, you would see, you get an impression about maybe this is how it tastes like, or you enjoy color in different life events, like in art, culture, and communication. It's a very impressive interface these days, color and the human. And in industry, color is one of the factors they evaluate as a quality check sometimes, and sometimes color is not enough. We talk about that. And in different life instances, like when you go to a signal, you look for color. You don't look for just a light to proceed further. So it influences in different ways. Just an example, color set the mood of a scene. Color set the mood of a room. For example, if it's all a moody climate, you feel it. And when you go to a museum, when you go to a gallery, you also experience color. And this can actually tell a story differently if you look at the color differently. So then the question that we are going to address today is, color is good enough to take decisions? So how you experience some objects looks differently in different lighting conditions. Maybe a simple example is you go to a textile shop, you buy something, and when you come out of the shop, you see that, oh, this is not that the match is not exactly what you experienced inside the shop, right? So this is very, very common. And there are plenty of different examples that you can actually correlate this with. Sometimes you and your friend or the next person see the color differently. So maybe there is something with your eyes, the sensor that you have. in your eyes is seeing things differently, or there is a different phenomena happening. Sometimes different materials, it appears to be the same. This is also that you experience. This is all connected somehow. And have you ever managed to identify the exact material just based on the color? Sometimes we would be fooled. Maybe a reproduced item and original fruit, for example. It may look very similar. And if it is from a distance, you may not be able to identify whether it is the exact original stuff or the reproduction. And sometimes the entire goal of reproduction is actually to prepare something which looks close to the object, close to the real object. So there are many cases where you can actually experience where the color is not good enough. The example that I mentioned, the metamerism, where same object or different objects look same in some lighting conditions, or different people could experience color differently in different lighting conditions. So these can actually impact whether we can use color as a factor for different evaluations. For example, in the industry, in a sorting machine, is color is good enough? Or for you to personally evaluate something, sometimes the health people, the doctors, would they be able to find out the disease just based on the color? Maybe color may sometimes fool us, because it all depends on where they are actually sitting, and whether they are in a room with certain lighting conditions, or they are in a different lighting conditions outside the room, or so this can actually create problems. So color is a perceptual construct, and based on the cone responses that each of us have, and each of us may have different responses, which will create the perception differently. And real world color perceptions are merely depends on only on these sensors, and the same applicable for different cameras. So it's not only human. Most of the normal conventional cameras, the conventional 3-channel cameras also could be fooled based on this metameric effect. And they are also not good enough to reveal the material composition. And it also missed some invisible information, because color is more focused only in the visible region. So whatever outside the visible region could not be perceived with the color. You probably have experienced in the COVID days, you have been monitored with a thermal camera, right? When you go to an airport or some places where you want to enter, you have been monitored with a thermal camera just to find out how much heat on your body, the thermal radiation. So this is something outside the visible region, or a normal camera or a human can see. If it would have been possible for a human could see that, they would not have used a thermal camera. So different situations, it says that the color is limited. Color is also limited for us to actually get some quantitative information from the object if you want to make a measurement. Sorry, my throat is not so good, so I will put some oil in between. So color is entirely based on the perception, and spectra, which I'm going to talk about, is more on the physics. So colors can tell us how things looks like, but the spectral information can tell us what they are. So as I said, in a normal camera, in a normal color imaging camera, 3-channel camera, when you take a picture, it generates 3 channels, red, green, and blue, right? And there are so much things happen when the light interact with an object. I'm sure that the whole audience, everyone is familiar with what things could happen. It can reflect, it can, the material could absorb the light, there could be fluorescence, the object could also transmit light, for example. So we have the glass in the room. So the glass transmit the light. So all different types of phenomena could happen when the light interact with the object. And it would be nice to document this for different purposes, for studying the material, getting more the physical or chemical composition of the material by using different instruments. And there, the 3-channel devices may not be good enough. So there we go for something called spectroscopy. And those who are with the optics or physics background, they know what is spectroscopy. We would try to measure the interaction of the light with the object over different wavelengths. And in spectroscopy, in order to perform the reflectance or transmittance or the absorbance spectroscopy, we use a device called the spectrometer. And depends on the range of the spectrometer, we would say that, okay, it's a UV, it has sensitivity in the UV region, in the visible region, NIR region, shortwave IR region, and so on. So these ranges I put here, it's not exactly there. In some books, you may see, okay, it's not 400, it's 380. So, but the boundaries may change a bit, but this is the range that we used to use in the sector. So in spectral imaging, what we are trying to do is actually combining the 2 different techniques, imaging and spectroscopy, to form something called spectral imaging. So the reason is that spectroscopy, even though it is very powerful techniques, it's mostly limited to points. So you cannot get so if you want to measure the spectrum of an object, you may have to actually sample the object and get the spectrum from certain points. It's not by default, it's not over the whole surface. But in spectral imaging, we combine with the imaging where it actually captures the whole spatial information. We try to combine this with a spectroscopy and we capture the information over the whole spatial area. So it's a combination, it's a combined version of spectroscopy and imaging. And so compared to the normal imaging where we have only 3 channels, in spectral imaging, there could be many number of channels. It could be 5 channels, 10 channels, it could be hundreds of different channels. So, and with having this number of different channels, we would also get the spectrum from every point in the object. So if it was just the spectroscopy, we would have information only from certain points, but in spectral imaging, we get the spectral information from all the pixels in that image or all the points in that image. What does it offer? It overcomes some of the limitations of the normal color imaging. For example, these cases, I have mentioned some examples where the material may look like same, but it would be different. So for example, here, you can see that, okay, cobalt blue and ultramarine, they looks very similar. I don't know, in the screen also, it looks very, very, very similar, but the material is different. So think about an example where you can mess up things. Assume that you are restoring a painting and you think that based only on the color, you think that, oh, this is a cobalt blue, and you apply something instead of ultramarine, you apply cobalt blue. You may not see any difference immediately, but if you bring that same painting to a different lighting condition, you will immediately see that, oh, there is some problem. Some problem happened. And then I will show you some of the examples that could mess up everything. So this is so important in the case of, in the application area of cultural heritage. You have to be very precise. Otherwise, all these examples that you have seeing here, you could end up in applying a different material for restoring the object instead of the actual material. So in spectral imaging, as I said, it actually it takes pictures from different wavelengths. And how many? It depends on the capability of the camera and many things. We could immediately classify based on the number of channels or the number of bands as multispectral and hyperspectral imaging. So multispectral imaging is normally between 3 and 10 channels, and also the channels are normally broader. And in hyperspectral imaging, we would actually take pictures in very narrow bands and very closely spaced intervals. Another important difference between normal imaging and spectral imaging is that in normal imaging, we do the imaging in the visible region. Most of the RGB cameras, or we call it RGB because it's sensitive to red, green, and blue, are limited in the visible region. But in multispectral or hyperspectral imaging, this could also, it's very normal to have imaging that is being done in the UV, IR, or in the shortwave IR or midwave IR or the longwave IR. Depends on where you are actually looking at, you get different information. So you get much more information compared to a normal visible camera. So information means that then you can do better interpretations. You can do more quantitative analysis. You can take better decisions. So this is a slide where you can actually see a direct comparison between a monochrome camera where you take only one grayscale image. Then you have a RGB camera which takes 3 channels or 3 images corresponding to red, green, and blue. In spectroscopy, it's focused on many points, many wavelengths, but only 1 pixel. And in multispectral, it could be 3 to 10 channels. And in hyperspectral, many hundreds of different channels. And you can see the summary of the things that I mentioned, whether it is limited to the visible region or how many channels, all this information. You could also see the cited articles in the bottom of the slides if you are interested to go deeper and read more about it. So this is an image of a tapestry which is being scanned in Oslo. So you can see at different wavelengths, different information is visible. And you can see this image from 400 nanometer to 2500 nanometer. This is being captured using 2 different cameras. And then you could get the spectrum almost with 500 points between 400 to 2500 nanometer. And this has been very useful for the conservators to identify the material, to restore the material, sometimes also this could be used for matching, find the right matching between different, it's like a puzzle problem. So there are different pieces of the textiles, ancient textiles, and this has been very useful in terms of finding the right matches. So as I mentioned, spectral imaging produces so many channels, and you can visualize like pages of a book. That's an easy way to visualize. So a normal camera produces a 3-page book, and a multispectral camera produces something like a 10-page book or 3 to 10 pages, and a hyperspectral camera produces hundreds of pages in a book. So that's an easy way to visualize, but the data may be represented inside the file differently. So there are different file formats. So I'm taking a bit to the history where this has been originated and how this has been progressed. So you can see a paper from the 80s where this has been used and it's been published in journal Science. So they say imaging spectroscopy has been very useful to identify the materials from each pixels. And in those days, they also already said that they have the airborne or the spaceborne sensors capable of producing 100 to 200 spectral bands. So this could also introduce some problems when you have so much of information. So we will come to that later. But as you can see, this is being started early days. So what are the specifications when you actually talk about spectral imaging? As I said, it has different spectral ranges. So you can say that, okay, I have a vernier camera. That means it's sensitive to visible and near infrared. I have a SWIR camera, then it's sensible to shortwave IR. 1000 to 2500 nanometer. Then mid-wave IR, long-wave IR. So different ranges. The spectral resolution. So in normal cameras that you say that, oh, I have a phone camera or a SLR camera. This has spatial resolution. 10 megapixel, 100 megapixel, and so on. But here we also mentioned the spectral resolution. How many channels? That's also another way to specify a spectral camera. What's the frame rate? How many frames can you capture at a time? The different detector type, as we are detecting light information in different region. Maybe our normal silicon sensors, silicon CCD sensors are not good enough. And there are different sensors, depends on which wavelength range we use the camera for. The digitization, how many bits has been used, different file formats. As I said before, how the file is organized, how the data is organized in a file. There are different file formats. You can get an idea about in terms of the numbers, and also there is different detector types. We will go more into details of different on all of these aspects. Different detectors. So the silicon CCDs are mostly used for the visible and NIR cameras. Do you know that your cameras you have, it is sensitive also to the NIR region? So if you have a RGB camera, most of the RGB cameras, the NIR is blocked with a filter. But it is possible to even physically remove the filter and make it sensitive to NIR region. So the silicon CCDs could be used for visible and NIR region. And then standard Indian gallium arsenide detectors are sensitive to from 900 to 1700 nanometer. And in many cases, when you go to the NIR region, cooling is also needed in order to reduce the noise in these cameras. So one of the cameras that we use in the lab, we actually turn it on a little bit before, like 10-15 minutes before we start using the cameras. Otherwise, this creates a lot of noise in the images. So this is very, very normal to have cooling that's used in the detectors. So you have to be very familiar with what spectral region you are using before you actually apply this on a case. So what are the different technologies used for collecting this information? You know, we are now trying to capture both spectral and spatial information from a scene. So that includes some of the complexities. So you can actually classify spectral imaging into different technologies. Point scanning, where you actually scan one point at a time, and then you move to the next point, you scan the whole wavelength region, and then you scan to the next region. And likewise, you go all over the pixels and capture the information. So that's a point scanning. Then line scanning, which is very common. It's also called push broom scanning, where you scan one line at a time. So you sweep it from one end to the other. So it's very common in airborne applications where you keep having the camera in a helicopter and then you actually move. We will come to that. We will go to the details later. Then there is something called whisk broom cameras, where you capture one band at a time, and then you go to the next band, and so on. And there is something called a snapshot, which is the fastest. You take one snap, and you get all the information. So each of this has its own pros and cons. The easy one that we start with is a filter wheel camera, where you have a filter wheel in front of a monochrome camera, a grayscale camera, and the camera captures one image when the filter comes in front of the sensor. And then after this the next filter will come to the in front of the sensor. It takes another image and so on. So in this one, you can see that, okay, 1, 2, 3, 4, 5, 6. So this wheel can actually enable the camera to capture, the system to capture 6 images. So it's a 6-channel multispectral image. So there are many pros and cons for each of different technologies. In case of multispectral camera, it takes long acquisition time because the filter has to move its position in order to take a picture. So the wavelength switching takes some time. Then the mechanical complexity. So there is a moving element, and this can also create a vibration. This can also create some misregistration because there is moving always requires some precision in order to get exactly this images at the same place. Limited spectral range and the scalability issues. So how many bands you can capture? So, okay, the camera that you see below, it has 8 filters. So you can capture only 8 bands. And if you want to capture something more, you need to change the filters. You need to physically change the filters. So it involves screwing, unscrewing, mechanically changing the filters. So you disturb the system somehow. Then the spatial misalignment between the bands. You know, each of these spectral filters that we use may have different thickness. This could also create problems. You know, light or not propagates always straight. So it bend depends on the thickness of the filter and many factors. So all this can create problems. So it's relatively cheaper. So there are also pros and for this camera. So this is one of the camera. We have this camera in Colourlab, the one on the bottom. It's from a company called Pixel Tech, and it has 8 filters. So this is one way that we use the camera. You can actually attach to a tripod. You keep the light sources, and then you have the spectral images. Another technology, liquid crystal tunable filters. It avoids some of the disadvantages of the multispectral camera with a filter wheel. It mainly works in the visible to NIR region. It doesn't go beyond the NIR region. It provides better image quality compared to the filter wheel, but it has also some drawbacks. So LCTF, where you actually control you can tune the filter, you can tune the passband based on the voltage that you apply to the liquid crystal tunable filter. And it doesn't transmit exactly the same amount of light in all bands. So it transmits only a fraction of incoming light. So there is an efficiency problem. And this can also create noise. Then slow spectral switching. So if you want to take some objects that moves faster or not static, for example, in medical imaging, if you want to take a picture of something moving, a moving organ, you cannot really use a LCTF or a multispectral camera, a filter wheel camera, because your organ may actually move. Or if you want to use it in a autonomous driving, you may not be able to use these technologies. So slow switching between the spectral channels. Then it's highly sensitive to the temperature. So you have to be, you cannot really use it in outdoors so much if the temperature varies. So I have to be aware that this is sensitive to the temperature. Limited to the spectral range. As I said, this is mostly in the visible and near IR. Then bandwidth limitations. It's typically broader than the normal hyperspectral cameras where it produces narrow bands. Then snapshot spectral imaging systems. So snapshot means just like your normal camera. You take one click and you get all the information in one go. So it offers a lot of good things. Normally the resolution is limited. That's the spectral resolution is limited. But it could be applied for, it could be used for things that moves faster. Even videos, there are cameras. So you could simply imagine it like an extension of, there are different technologies, but some of the most commonly used ones are, you could imagine it like an extension of the color filter arrays that you use in your cameras. So in color filter array, the Bayer pattern, which reduce the resolution, and then you pre-process, do the demosaicing to produce the resolution. And here, instead of only the RGB, you could have more sensitive elements. on different spectral channels, and that makes it a multispectral filter array. This could be used as a snapshot imaging device. So the problem is that when you actually increase the number of channels, you reduce the spatial resolution because they are directly correlated. So there are different versions of multispectral spectral filter arrays available, sensitive to both visible and NAR region. This is just an example where you have the filters arranged in different patterns. So one on the left actually having 8 different filters, and which is visible, sensitive to the visible region, and one on the right, 8 on the IR region. There are many different technologies available. There is also snapshot systems available with micro lenses, which actually does the filtering operation. Then another commonly used one is the line scanner. So line scanner is very popular. We have 2 of them in our lab, one in the visible region and one in the shortwave IR region. So as I said before, it's also called the push broom. So it's basically like brooming. It's like brooming from one end to the other. So you do the sweeping. So if this is your object, you take one line at a time, and then this object or the camera moves to the next position and it takes another image. And at the end, if I want to scan the whole object, either this object has to move this many positions, or the camera has to move from one end to the other. So there is a moving element, either the camera or the object. We see some examples. And again, like all the other systems I mentioned, different pros and cons. It produces high resolution. The resolution depends on, normally the spatial resolution depends on how many points. So if my camera can move more, then it can produce more spatial resolution. Then it also offers a high resolution, a high spectral resolution. So it's much efficient use of light compared to the other cameras. The noise SNR is high compared to the filter-based systems. It's well suited for large areas and continuous scanning. As I said, you can actually attach to a helicopter, and the helicopter can move many meters or kilometers and can capture the image. So the spatial resolution depends on the movement. And it's very mature. It's a very widely used technology. Then the cons, since there is some moving elements involved, it has to have some precision in the movement. Otherwise, you can actually end up in messing up the spectral and spatial information. So motion artifacts, it's normal if you don't control it properly. Not ideal for dynamic scenes because there is moving element. So by the time you move to the next position, maybe the object would move. So it cannot be used for scanning dynamic objects. Longer acquisition time compared to the snapshot. Of course, the snapshot takes the image in one shot. This is the basic arrangement of different elements inside the camera from the scene to the sensor. So there is always a dispersive element involved, which actually split the light into different wavelength components, and then it goes to the 2D sensor. A more detailed version of the same. I will share the slides at the end, so you don't need to make notes now. You can get all this information. So the coming slides show some of the examples of the push broom systems. In this case, the camera is moving, and the object or the scene is basically a painting, which is attached to the static setup. So the camera moves up and down, and it sweeps, and it captures one line at a time. So this is another system where the camera is static compared to here. Here the camera is moving from top to bottom and in both X and Y directions. And then it takes the picture. we need to actually stitch the images at the end if we have a larger object. So in this case, the camera is in the same place, but the object is moving. So you keep the object on a moving platform, and this platform will move. And this, most of the cameras, there is a link between the integration time or the exposure time and the movement of the platform. So if you keep a dark object, like in a normal photography, when you have a dark object, you need a higher exposure time or higher integration time. And higher integration time means this platform will be moving slower. And if it is a really bright object, you don't need so much of exposure, then it can move faster. This is another type of, another way of capturing with a push boom scanner. Here the camera is attached to a rotating arm, rotating tripod, and the tripod will sweep from one end to the other. So depends on the situation, we use different technologies. So in this case, we could actually bring the painting and attach to this object, or the painting could be just in the wall, and I can set up the camera outside the painting, and I could do the XY scanning. This kind of setup could be used in a, for example, if I want to scan a manuscript, I could just put the manuscript on this platform and do the scanning. And sometimes I was scanning in a museum, and in most cases they don't let you take the painting from the wall. So you have no choice. You have to capture it somehow. And then I have used a camera on a tripod. And so like in every case, every imaging, it's not just the camera that captures. You also need some other elements like lighting. And the lighting has to illuminate the scene, which is matching with the spectral region of sensitivity. So if you want to capture something in the IR region, you have to expose the scene with the light from in the IR region. This is also a problem sometimes, because if you want to capture things in IR region, then you also expose the object with the light, with thermal light. Some examples are the examples. I am scanning some fruits, and here I could put the fruit on a tray and then do the scanning. The second one, again, another example where you can actually use it on an XY stage. This is a system used by the MoLab. Have you heard about MoLab? So this is a European facility that could be, you can apply and get the camera and the acquisition at your place. So they used a system like this, where the camera and the light source moving at the same time. You can see that the light source is attached to some arms in 45 angle, and then it moves. So the examples I have shown you is mostly in lab setup. But then when it comes to, so spectral imaging is originally developed for remote sensing and satellite imaging. And there the situation is even much more complex. You can have the light path from all different objects around, and your light source here is sun. So if you're capturing something, you have to be careful about the situation. It may be a sunny day, it may be a cloudy day. So these all could produce the result differently. And you may not have a reference. So here you can see that I have kept a reference, a spectral on tile, close to the object. And in case of a remote sensing case, you may not have a reference covering the entire area or covering the entire scene. And you have light that come from many different directions, many different objects could be reflecting light to the camera. So now we have seen 4 different cases where you have a point scanning, a line scanning, a whisk broom scanning, and a snapshot scanning. So point scanning, a dispersive element bring the light to one point. In case of a 2D detector, like a line scanner, where you have a prism which disperses to a 2D array of sensors, and then you capture one line at a time. And then cameras like multispectral, the filter wheel camera, it can capture one band at a time, and the snapshot devices, or with the micro lenses or with the multispectral filter arrays. It's a summary slide where each of these different technologies has been compared with its pros and cons. So each of these could be applied for different settings. All depends on which application area that you use. If you want to capture something very moving stuff, then you need to have a snapshot device, or if you are capturing something, if you need something high resolution, then you need to have a push broom scanner. So it depends on the limits and what you need. You need to choose the right technology. And of course, the budget also matters. Each of these has completely different range of prices. So as I said, different factors could influence what you choose for a specific application. So it depends on the instrument architecture. A simple example: if you're planning to use it in machine vision settings where you want to do some sorting, maybe in an industry setting there is also heating problems. So then you need to be careful about okay, this sensor is sensitive to heating, and in different heating conditions it can produce different spectrum. So then it can produce problems. So there are different factors that can influence the choice of a spectral imaging system. So what are the elements? A review. What are the elements of a spectral imaging system? There is an optics which bring the light from the scene to the sensor, and in between the scene and the sensor there is a dispersive element which will split your light into different components. And then there is a processing unit, and we also use different references for converting the light into its reflectance or transmittance. We also use references in order to have correct geometrical object captured in the scene from the scene, and the right illuminant, which could actually influence your data, the quality of the data. In case of a remote sensing, sun is a light source, but in other cases you have to have different light sources. So this is a generic signal chain for a spectral camera. The first part you don't need to go more detailed into but just to understand, the first part is the hardware, where you actually get the light into the sensor, and once the light is being captured in the sensor, you need to do some corrections, like in a normal camera. In normal camera, many cases it is part of the business. It's already there in the system. And in spectral cameras, in many cases, you need to be aware of what is happening, what are you capturing, and based on that, you need to do the corrections. Some corrections like dark current correction, I will tell you that what it is. And then at the end, you get corrected radiance image. We convert that into the reflectance using a reference. Different systems. I show you some examples of different systems. This is one of the portable hyperspectral cameras that we use. It has some advantages and some disadvantages. It's very portable. That's the advantage compared to many systems. It's a line scanner system, even though it doesn't look like a line scanner. Inside the system, the mechanism is line scanning. The main disadvantage of this system is the low spatial resolution. So if I take a picture from a distance, you may get a lot of blocking artifacts. This is one of the latest updates from last year. Smartphone cameras go hyperspectral. It's not only from these guys in Purdue University, but also from other places. It's happening. So there are many disadvantages, but it gives a lot of power to each of us in terms of. I'm sorry. It gives the spectral cameras in your pocket, and it would be much useful for many different application areas. This one, a German company producing a camera called the Cuberts. It's a video hyperspectral camera, mostly in the visible region, but 125 bands and captured real time. So these kind of cameras could be used for real time application like autonomous driving or scanning from the drones. Underwater hyperspectral camera. So these kind of cameras could be used for classifying different things happening under the water. We have, so this camera is a spin-off from NTNU. They have different versions, and some cameras offer from going to a depth of 300 meters. Some of them actually goes even to 2 to 6 kilometers. So it can be used for much deeper applications. On the right side, you see a camera including the light source. So this is a spin-off from Department of Cybernetics at NTNU, and they have been using it for different applications. Last year, they have been scanning it attached to a robot and we have a lake close to the campus, and they have been looking for some shipwrecks in the bottom of the lake using this camera. Of course, when you actually go down, you could also get a lot of distortions in the image. So this is a mesh and a color checker under the water. And one of the COSI students, he did a project on creating a database for underwater hyperspectral images. If you want to get the data, you can actually follow the link and download the data and use it. So then this is another multispectral sensor going to be part of phone or mobile devices. This is a development from SONY. SONY Europe is working on that. And one of the COSI students defended last year, she actually did her master thesis in SONY on multispectral camera development. So there has been a lot of companies now in the market offering the hyperspectral systems. We have a couple of cameras from different companies. We have HiSpecs, it's a Norwegian company. Their focus is more on line scanners and on different application areas, mining, remote sensing, UAVs, and so on. Specking, Finnish company, Headwall, Ecoton, it's a Norwegian. So there are many companies in the market now on the development of different commercial systems available. So yeah, I'm not going deeper into the different stages, but I just want to mention what are the workflow, how from capturing the data until you get the reflectance cube, the spectral data cube. So you capture the raw spectral cube, and in many cases you need to do some dark current subtraction. So I'm sure that all of you know what is dark current. So dark current is something the signal produced in the camera when there is no light. So normally, if you want to capture dark current, you close the camera with a lid and then take a picture and use it as a dark current. And when you start processing, the first thing that you do is subtract this dark current, because this is not part of the real image. You subtract the dark current from the image and use the image into the next stage. And you need to be aware that you need to capture the dark current in different exposure, even though there is no light. And you need to capture the dark current in different wavelengths, in all wavelengths. Then the sensor characterization, there would be some sensor corrections that you need to be done. Illumination correction, it depends on the illumination that's seen. It could be very uniform. It could also be, you may not be able to cover the entire scene with a reference target. Then you need to perform some illumination correction. Then spectral calibration. Normally we do that with a spectral on tile or a white reference. And geometric corrections. In many cameras, due to the complexity of the sensor and 2D array and diffraction mechanism, everything. When it all comes together, it could create a lot of geometrical distortions. And when you start processing the data, you will actually come across these distortions, which will stop you from stitching different stripes of an image, for example. If you take different stripes in an image, then it would be difficult to stitch it together. So yeah, it's an extended version of what I just mentioned, the dark current, different stages. And the main thing in a spectral image is the reflectance calculation. So reflectance calculation means you need to measure the amount of light in order to convert the radiance to the reflectance. And reflectance is very commonly used in spectral imaging. And in order to convert, or in order to measure how much light is being you have exposed into the object, you need to put some reference object, and the most commonly used one is a spectral on tile, which will give you the exact value, how much light is into the scene. And here you can see a multi-shade spectral on tile. This is being used because if you want to capture something very dark scene, you normally put a high exposure time, right? And when you put a high exposure time into a spectral on tile, the white part will get saturated. So saturated information you cannot use. So it depends on how is the scene, you use different part of the shade. So that's the use of a multi-scale spectral on tile. And if there is no spectral on tile, you could also use some white references. Barium sulfide is also been, it's very common to use barium sulfide for different applications. Color checker is being used, and in many cases we use also a geometric target. I use this one, a mesh image of a mesh into the scene so that I get an idea about how much distortion is happening geometrically into the image. Different processing methods used, basic operations. So once you have suppose you have 100 channels that you have already captured. So what can you do with the data? That's also important. It's not only capturing the information, the right processing step has to be followed in order to use the data. So you can use simple operations like multiplication, division, etc., and band ratio, which is very commonly used. Statistical operations like PCA, ICA, MNF, different spectral classification algorithms, classifying the material based on the spectrum, spectral information, dimensionality reduction, spectral unmixing, etc. I come to this more when I talk about the application. Talking about the quality of the data that you capture, some of the key parameters. One is keystone effect. So keystone effect is a spatial misregistration. So that means there could be different magnification in different bands. And that is called keystone distortion. So when you actually buy a camera or characterize a camera, these are some of the factors that you need to be aware of. So you can see that in the left side, there is no distortion. And in the keystone distortion, different spectral bands are magnified differently. And there is something called the smile effect. Smile effect is a spectral misregistration. That's a wavelength shift from one band to the other. So smile effect, it's easy to remember. Smile effect could distort the image like a smile. So you can characterize smile and keystone effect using a input slit with various laser wavelengths. Then you can see the shift in the wavelength, and keystone with a different slit width. How to visualize the spectral image? In a RGB image, you have only 3 channels. So you can actually, it's a color image that you get as a result of the 3 channels. So when you have 100 channels, which 3 channels will you pick to produce the RGB? You cannot visualize more than 3 channels. So the simple way is to actually pick any 3 channels and make it as a RGB image. Or pick it close to red, green, and blue. Then it's close to a RGB image. So then you can also apply some color matching functions to make it a true color image. Then band-wise, you can actually visualize the spectral image band by band. So you can have the first band, second band, and so on. Then you can use some statistical operations like PCA, get all the information into a couple of bands, and use that, visualize those bands. And as a spectral cube, as a 3D cube, you can visualize. I also give a link to different visualization tools available. So you can use, you can check different tools available. I mentioned in the very early stage that, okay, when you capture a spectral image, you also create a lot of data. So having a lot of data, maybe some of this data is redundant. So why do I need 200 or 500 different images when the same information is available in maybe in 10 different bands? So I need to apply some algorithms in order to pick up the right bands which give you the most information. So there are different dimensionality reduction algorithms available. Spectral library, I will talk when it comes to the application. So what are the main challenges? One is the huge amount of data, lack of standardization. There is some attempt on that direction. I will tell you later. Quality evaluation for a RGB image. If you take a picture with a normal camera, you can check it. You can actually see, oh, okay, it's very sharp. It is very bright. It is different attributes that you can check. It's, oh, this is a good image, right? You can tell. You perceive the quality of the image. It's mostly subjective, or it could also be objective metrics could be applied. But in when you have hundreds of different channels, which 3 channels will decide? So you cannot really use visualization to say that this is the best spectral image. Then different file formats, lack of dedicated software for different applications. That's also a challenge. Image registration is a challenge when you have images come from cameras with a different resolution. That's a problem. So in our lab, I use a veneer camera which produces 1,600 pixels, and I use another camera with just 380 pixels. So if I want to fuse these 2 images registered together, then I have 2 images with 2 different resolutions. That's also a problem. So some of these problems are already identified even in the early days. So storage of massive data is a big problem, and the processing of it. So where spectral imaging is going? So as I said, there are a lot of different commercial companies producing cameras. So more portable systems are coming. Integration of more AI and machine learning or physics-based models are available. A lot of cross interdisciplinarity learning from one sector to the other. So I work in cultural heritage as well as in food and also in forensics. So all these different domains, I could use the same, sometimes use the same algorithm. I just need to be aware of what I'm doing. Open challenges. So I mentioned there is some attempt towards standards or for characterization of hyperspectral imaging systems. This is a report published by IEEE very recently, June 2025. So you can download. It's like 150 pages, and which tells you what you need to be careful about when you characterize a camera, when you buy a camera, what specifications that you need to be looking into. So the conclusion, I come from Colourlab and I talk about color, but I say that colors are not good enough. So we need more information, and that could be done with spectral imaging. And there are different challenges and opportunities for spectral imaging. And it has been finding, it has been a lot of different application areas are developing for the use of spectral images. So I stop here and then we play a Kahoot before I go to the next topic on application of spectral imaging. So have you guys played Kahoot before? So it's simple questions. So you get a number here now, or you scan with a QR code. Then I have a couple of questions. You can play a bit and see you learned something now. By the way, Kahoot is a tool that is being developed in my department at NTNU. So it's a very popular tool. It is one of the very successful spin-off from NTNU. I see a Messi sitting in the audience. It seems we are 84 now, 85. Okay, then we can start. Okay, very, very smart guys. We move on. Wow, I'm happy that the lecture was okay. Where are these 27 guys? We move on. Oh no, I was talking a lot about this. It should be correct. Okay, we move on. Let's see. Uh, so the last thing I mentioned, spectral on tile. Wow. I haven't really mentioned about this. Let's see how many of you actually know what is spectral unmixing. So I can skip those slides in the coming session. Oh, it's a push broom camera. Okay. Some people are sleeping in the last part of the lecture. Yes, let's go. I will show you some examples of this in the coming session. Same people, I think. Very good. It's a repetition almost. Very good. The last question. Oh, you think that it's the same? 24 people think that it's the same. No, but it's a bit different. So you're done. Let's see the final score. Oh. Do you want to stand up? Who is that? Oh, very good. Congratulations. I don't have a gift. The organizer will give you something. Okay, very good. We will then continue. So I start the second part with a little bit about the application of spectral imaging. I'm not going to talk about all different areas, but you see, it has been used in many different application areas, starting from remote sensing, satellite, food, agriculture, biometrics, autonomous vehicles, industrial applications, forensics, a lot of application areas. But in this session, I will focus only on cultural heritage and food. So as I said, this is a technology started from the remote sensing field, a lot matured in the remote sensing, and where it is being used for classifying different elements in the land, like soil, water, minerals, the vegetation, etc., etc. And then we bring the camera, we bring the same science into the lab in a proximity or close range imaging, and see how this could be useful, how this could overcome some of the challenges. Let's see how this could be used in cultural heritage. There are many motivations, and this could solve many problems. So in cultural heritage, it's so important to have high resolution, both in spectral and spatial, in order to document different objects. So there we can actually apply cultural heritage, we will see. Hi-fi reproduction of objects, so which will overcome the problems that could happen with the normal conventional cameras. Investigation of under drawings or under paintings, things we cannot see with our eyes or normal cameras, but the spectral cameras can see. Another important application is a non-destructive identification of the materials, virtual restoration of objects, and studying the effect of different ambient lights. So I start with something. Have you seen this painting? Yeah, this is an incident that happened in Spain. Even though it went in a worse restoration, after this, there has been a lot more visitors than before. This was also in the news recently. It was just 2 weeks ago. The restorer, she died. So it was in BBC about this news case where this person has died. But this is a very famous incident that happened in 2012. This is also a couple of years back. This incident that has happened where the restoration has been done without aware of what they need to clean. And then it ended up in over-cleaning. In many of these cases, this could have been avoided if there was a possibility for a virtual restoration before they actually applied on the restoration on the real object. So there has been a lot of such activities happened. And then going back to the history, in 1989, this project called Vasari, the Visual Art System for Archiving and Retrieval of Images, the main goal was for preparing a colorimetric scanner for direct digital imaging of paintings. So more on the color accuracy. That was the main goal at that time. The system was focused more on the visible region. And later, this has been updated. Then this has also been, the goals has changed, also used for the possibility of conservation and the damage assessment, and more for the documentation and publishing, etc. And Chrysanthal, this is another extension of same, but here there is also a focus towards outside of the visible region. So if, out of these 11 different bands, 3 of them are actually in the NIR region. So there has been a lot of projects on this area, started from the 80s. We also had a project, me and Alan Tremo also. I think the first time we met is on a project called COSH, Color and Space in Cultural Heritage, where different aspect has been considered, 3D, spectral, spatial, etc., etc. So towards the color accuracy, it has been there has been many attempts to say that okay, spectral imaging produce or document the colors more precisely. So then this could be used for hi-fi reproduction and also avoiding some of the metameric issues, like I showed you. Okay, if the painting reproduced in different conditions, different lighting conditions could appear differently, then that's a problem. How can we actually reduce such problems? Then spectral imaging on the famous painting, The Scream, where I have actually involved. We have actually done the pigment classification of the painting. And in this case, this same painting has been studied before at the National Gallery in Oslo, where they have actually picked up the pigment from different locations of the painting. And then they did the chemical analysis to identify what pigments is being present. And in spectral imaging, when we did the spectral imaging in 2013, what we have actually used is exactly the same points. We use the same spectrum in order to do the spectral classification in different areas of the screen. And you can also see the second image is actually the backside of the screen. You don't see that when you go to the gallery because it's attached to the wall. So in every case, one thing that we need in order to perform a spectral classification is we need a spectral library. In this case, I could obtain the spectral library from the chemical study that is being done before. We could also use some external pigments, external library, but then there is always a problem. This is sometimes it doesn't match with the age, doesn't match with all the things that happen over the time for very old paintings. These are some of the different libraries that we have created. This has been created by one of the COSI student, CMET student called Federico Glini. Later, he did his PhD at NTNU, and now he is a postdoc in Copenhagen. So he has actually used, he has created a spectral library, mixing different Kramer pigments with a non-ratio. So he knows what he put in different places. And the data is available if some of you actually want to try this. It's openly available. So then we tried different spectral classification algorithms to detect the pigments. And you can see that how two different algorithms, they are performing differently to classify two different pigments, vermilion and a red color, unknown red. It's a lead white and vermilion. I also want to mention that different classification algorithms could actually end up in different classification, different results. So we need to have a ground truth if possible, which is difficult in many cases. So visualization, it also depends on the penetration of the light, which spectral range you are using. So if you are using a UV, you get more about information about the varnish and the surface. When you are in the visible region, you see what you are actually seeing with your normal eyes. The more you go to the IR penetrates, and then you get underdrawings and more information about the frame. If you go further in terahertz, even you get details about the canvas. This is a false color visualization of a painting. You can see that, okay, even with the false color visualization, not with much processing, still you would be able to classify some of the materials, which looks very similar in a normal conventional camera. So colors can fool us. So this is a false color image of the screen that we captured. Here also we could see something different, something more than what we could see with a normal color image of the painting. So there is a hidden message in screen, which is somewhere in the sky. So they could not really see that before very clearly as what we could read it here. So things could be much visible when we use IR imaging. I have mentioned about visualization. So we could also simulate the painting, how it looks like in a different lighting conditions. So if somebody is moving a painting for exhibition from one place to the other, they don't need to physically change the light in order to see how the painting looks like. And sometimes this could also set a different mood. This could also end up in having different pigments or objects looks like the same in some lighting conditions. So in order to perform this, we don't need to physically change the light. That's an advantage it offers. You can also see, okay, the same painting. This I captured in a museum in Lillehammer in Norway, close to our campus. And you can see that how this looks like in different elements. If you want to play with this, there is a library available. It's from the National Gallery in London. You have the spectral power distribution of hundreds of, more than 100 different light sources. So you basically apply the SPD of different light source, and you can visualize how this would look like in that specific lighting condition. Visualization tools, something very specific for cultural heritage. I have mentioned two tools here. You can actually play. I'm not showing a demo, respecting the time. We move forward, but you can actually look at these tools and see how this works. It's a direct application of spectral imaging. You can simply search IIP image viewer, and it's an open tool. Bosch project is a tool from the Rijksmuseum. It's not openly available, but you can try different possibilities. Virtual restoration. There is an activity on the virtual removal of varnish from Mona Lisa. So I'm not going to the details, but you can see that how they performed the virtual varnish removal of Mona Lisa. There is different reports available, publications, and YouTube videos on this topic. They actually simulated at different areas of the painting, and they also did the virtual aging of the varnish. So this is what something putting a light into what I said in the beginning. It's possible to do this virtual thing before we actually do physically on the object, which saves a lot of things, lot of history. This is about the virtual aging of the varnish. Crack detection. Sorry. Crack detection, another interesting thing, when you actually move the painting or the object from one place to the other, this can also undergo a lot of changes. And some of these micro changes, it won't be able to capture with a normal camera. And this could be documented before and after an object is being moved, or due to climate or different factors. So this is another advantage it offers. This being used a lot in the different libraries and old manuscripts. There is a famous Archimedes project. This is something I've done with the National Library in Oslo, where the challenge was to actually, there is a document which is being written in both directions, how to take it only one direction, so which improves the readability. So that could be done. Sometimes it could be done simply by just taking few bands, then you can actually remove. And then in manuscripts, one problem is the bleed through. Bleed through also could be removed easily with the simple application of spectral imaging. Then we just concluded a project last year called Change, Cultural Heritage Analysis for New Generations. The main idea was to actually how to monitor change in different objects. So you capture something now and you capture something 10 years after, and can you actually quantify the changes that is happening in the object? So that is the whole idea. You can think about something simple. Okay, you take image of something exactly in the same condition, take the image 10 years later or before, and then just subtract these two, you may get some changes. But ideally, this has to be in the same settings. But the lighting could, in a normal imaging, the lighting could change, the technology could change. So, but spectral imaging offers much more advantages. So we had many projects, 15 PhD students worked on different directions, not only spectral, but also in other directions. Most of them, almost all of them, graduated, except Alexandra. She is going to. So this is just finished. And one case study in that I want to mention is that we have done something with the Swiss National Museum, hyperspectral imaging in the gallery. In Zurich, we have actually used the Specim IQ camera to gather information about the stained glass windows. Then this is a real world operation where there is a lot of sunlight that come from, and a lot of vegetation from the background. And here we used reflectance, not reflectance, transmittance imaging. Another project which is going to be starting end of this year, from December 2026, and there will be 12 PhD positions, more on terahertz imaging. This is coordinated from France, but we will have one position in Norway. So many countries involved, including Italy, Denmark, France, Norway, etc. So visit the website, those who are interested. Quickly, in 3 minutes, about spectral imaging, how this could be used for food and agriculture. One of the main things they do in agriculture is also a sorting operation. When they get different things, either in the farms or after the post-harvest. So how to use spectral imaging for seeing things better. So we could do imaging with the spectral cameras. It's non-destructive, non-contact measurements, but at the same time, you would be able to get different properties of the fruits or vegetables. Multiple objects can be captured at the same time. It's suitable for rapid and large-scale fruit analysis. So it is possible to detect the foreign particles, so the quality aspects of fruits and the food inspections. Food grading, you can actually get different parameters. For example, sugar content of a fruit. I want to measure the sugar of a strawberry. This could be done with the spectral imaging. So what we normally do is we actually measure it with a SSE measurement, and then we also try to measure the spectrum, and then we try to correlate. So we have done on different fruits, strawberries, then the bruise detection, different fruits. For example, strawberry, it's very sensitive. Avocado, everyone, when you go to the supermarket, you press it and see whether it is ripe or not. And then sometimes you leave it. And some unlucky guys, they come later and they pick it. So how can we use it? We actually made the bruise physically, and we measured in different time intervals. And we also measured the spectrum at different time intervals. Then we tried to correlate this. This is one method to make the bruise. You have a pendulum. You leave the pendulum and hit on the fruit, and then it creates bruises. It won't be visible immediately, but after a day or two, it will become visible. This is on raspberries. We have been doing that in the real world, in a poly house in Norway, on different raspberries, and we wanted to measure the ripeness and also the sugar levels of raspberries. We were doing it in the room as well as in the real world condition. Kiwi is another project that we have done. We measured the sugar levels and the acidic levels, and then we tried to correlate. I'm moving a bit fast just to cover different. So this is the condition. We measured the kiwis in the lab. We have data for 500 kiwis, which has been measured in different conditions. You see that the room is dark in order to avoid any X-ray conditions. Then we did the bruise analysis of plum. So these are some of the examples. Here we actually use another different method to create the bruise. We drop some weight from the top to the fruit. So the summary is that you need to be aware of what you're looking at. So the spectral region is important. Then the techniques that you use important. You cannot use everything for everything. So this is a table which shows what kind of spectral imaging modality is used, what kind of technique is used for classification, which spectral region is sensitive. For example, the same technique that you use for apple may not be used for plum or something different. At industry scale, this is being used for scanning fish to see the quality of fish. I cannot play this outside Norway. This is from the news channel. But the fish is basically going on a tray, and the camera is on the top. So it's a line scanner. So it's an industry setting where the fish is moving, and the scanner real time. It is actually measuring the blood levels and the spectrum, and to say that what quality the fish has. This has been installed to evaluate the quality of salmon. Plant phenotyping. This is also a very popular area. We have actually a project on plant phenotyping now. So this will basically measure the height, the leaf area, biomass. It's not just a spectral imaging. It's also a combination of different modalities. It's from a company, but the solutions that they provide offers measuring all the possibilities, scanning with 3D scanners, spectral cameras of different range from shortwave IR, midwave IR, visible and near IR to check different properties of the plant. So we have a project called pheno.no. It's an infrastructure project for phenotyping in Norway. So there we also use a lot of drones to scan the field with spectral cameras and to do the phenotyping. It's a service offered to the community. So if a farmer want to do, we will actually go and scan the region and we provide them all the information. So I conclude my session on spectral imaging and application with the one slide, which is I have taken from an application area of autonomous driving, where you can see that this has been advantage with everything except the current cost. So the cost is the main factor which is stopping to apply in many different areas. Otherwise, this would have been much faster, even faster than now. So thank you very much. If there is any quick questions, I can answer just to respect the time. Otherwise, I'm so thankful for the organizers for inviting me and to meet all of you. Thank you, Alain, thank you, Pierre, and everyone. Thank you. My contact is available here in case if you want to contact me something. And I also, maybe there is a possibility for you to come to Norway and do an internship in my lab or in our group.
Let me start, SONY, by a question related to, I don't know if you work with multispectral or hyperspectral system embark on a drone, and for which kind of application, and what are the current issue in this field?
For the phenotyping.
Yeah.
Yeah, for the phenotyping, one main issue is there is a lot of quality parameters that we need to take care of. And we cannot have an external, the only external light source is the sun. So we can do the scanning only certain time intervals, like cloudy days better between like, okay, depends on Norway. From sometimes it's sunny all the day, but normally they do the scanning from 11 to 2 o'clock. So it's a limited period that we can do the scanning. And also the challenges in the data quality, because the plant is growing. So if I want to compare something from this week to next week, the plant would be growing, all the conditions would be changing, and also the interreflections, different plants could also influence the other plant. So there is a lot of challenges compared to the video I have shown. It's a very ideal condition. So that's the main, data quality is the main challenge.
Okay. And concerning the sensors that you use, how many bands or what is the spectral resolution of these sensors?
I don't remember exactly, but I can check it and let you know. Yeah.
Okay.
Yeah.
Thank you.
Thank you. Okay, then thanks again. Enjoy the coming days.